안녕하십니까. 저는 근본 추계 학술대회 공동학술위원장을 맡은 AI연구원의 김승환입니다. 이번 순서는 LG 플래너리 톡 세션으로 AI연구원의 Chief Scientist of AI이시자 미시건대 교수로 재직 중이신 이용락 교수님이십니다. 이용락 교수님은 IEEE가 선정한 세계 10대 AI 연구자입니다. 서울대에서 2003년 물리학과 컴퓨터공학 학사를 받으셨고, 스탠포드 대학에서 2006년 응용물리학 컴퓨터공학 석사를 받으셨고, 2010년에 컴퓨터공학 박사를 받으시고 2010년부터 미시건 대학에서 교수로 재직 중이십니다. 구글 브레인을 거쳐 현재 LGI연구원의 Chief Scientist of AI로 연구 활동을 주도하고 LG그룹 전 계열사의 디지털 트랜스포메이션에 기여하고 계십니다. 오늘 이용락 교수님의 턱은 Learning Representations and Models of the World for Solving Complex Task라는 주제로 영어로 진행될 예정이며 질문은 한국어, 영어 자유롭게 해주시면 됩니다. 이용락 교수님을 모시겠습니다.
예, 안녕하세요. 먼저 간단하게 인사드리겠습니다. 이홍락이라고 하고요. 영어로 발표를 하겠으니 좀 양해를 부탁드리겠습니다. 그리고 나중에 한국말로 질문하시면 한국말로 답변 드리겠습니다. Hello, it's my great pleasure to give a talk at Korean AI conference, and thank you so much for inviting me. I'm Hong-Lak Lee, Chief Scientist at LGAI Research and a Professor of Computer Science at the University of Michigan. Today, I'm going to talk about learning representations and models of the world for solving complex tasks. First, I'll present my recent research on this topic and later introduce what we are doing at LGAI Research. 화면 쉐어가 지금 혹시 됐나요?
화면 쉐어가 안 되고 있습니다.
예. 그러면 다시 해야겠네요.
네, 이제 보입니다.
예, 알겠습니다. 네, 그럼 다시 하겠습니다. Hello, it's my great pleasure to give a talk at the Korean AI conference, and thanks so much for inviting me. I'm Hong-Lak Lee, a Chief Scientist at LGAI Research and a Professor of Computer Science at the University of Michigan. Today, I'm going to talk about learning representations and models of the world for solving complex tasks. First, I'll present my recent research on this topic and later introduce what we are doing at LGAI Research. There has been tremendous progress in AI, especially in the field of deep learning. Mostly, this progress has been thanks to development of large data sets, large-scale parallel computing devices such as GPUs, and large-capacity deep learning models and efficient learning algorithms. For example, deep learning-based computer vision systems can visually classify objects better than humans. AI systems are being used for autonomous vehicles, robotics, factory automation, to just name a few. This success is largely due to supervised learning from large-scale labeled data. So, does it mean that we have solved all the problems in AI? Of course not. From a research point of view, there are still many unresolved issues with current AI methods. For example, many AI algorithms lack ability to understand and reason about the world. Second, learning optimal behaviors in the environment requires a very large amount of data and/or experience, which means it is often difficult to learn from small amounts of experience. Finally, they lack the ability to perform complex tasks in a variety of scenarios, going beyond simple tasks. As a motivating example, let's imagine how awesome it'll be if we have a robot at home which can do all daily chores for us, such as tidying up the house, cooking, cleaning dishes, doing laundries, and so on. But it's extremely challenging to develop such a robot because it has to adapt to different home environments it was never trained on, and it has to perform huge variety of complex tasks according to what human users want. Another example is personal AI agents that can automatically perform lots of tasks for us, such as shopping, scheduling, communication, reading, writing, and so on. Developing such an AI system is extremely difficult, partly due to a large variety and complexity of tasks, depending on user preferences and constraints and other factors. Towards solving this problem, my grand research vision is to develop an AI agent that can perform many useful tasks for human users with high sample efficiency and strong generalization ability. So what do we need to get there? Such an agent needs to take actions in the environment by combining several abilities. Specifically, it will need to understand the data in the world by grounding vision, language, sensor data, and so on. It also needs to build a proper abstraction of the world by learning representations. And it should explore the world and task space efficiently, especially for complex and challenging tasks, and generalize robustly to previously unseen task scenarios, and learn and grow skills by composing previously learned skills. So today I'll tell you about 3 directions of research I have been working on recently. First, how to learn representations and models of the world, and to plan and act efficiently with this model. Then, how to learn representations so that the agent can explore and generalize more efficiently. Finally, how to develop the ability to solve difficult problems by combining existing learned skills. So here's the outline of today's talk. Let's begin with the word model. To train a model about the world from data, there are several approaches, but in this part, I'll start from a generative modeling perspective. The generative model provides a way to explain the data by learning latent variables that constitute factors of variation. You can also train models that connect multimodal data, such as text, image, video, voice, and other types of data. Finally, it can use unlabeled data efficiently in the form of self-supervised learning. In terms of applications, generative models can be used to create new data or to modify existing data, and such augmented data can be used to improve the recognition performance of downstream tasks. By predicting the future through video, we can train a simulation model based on the data, which helps agents to plan and perform actions efficiently. So in today's presentation, I'll talk about video generation research I've been working on recently. Predicting video in future frame is extremely challenging, as there are many factors of variation that make up the dynamics of how frames change through time. In this work, we developed a stochastic convolutional recurrent neural network and scaled the model size to learn complex dynamic patterns in videos. The main ingredient of success was to identify the core inductive biases and to scale up the model size. The resulting model can predict future videos quite well on several domains, such as human motions, robot-object interactions, and car driving. In our recent iClear paper, we studied how to further improve the video-based word model. For complex scene-level video data, such as car driving, the previous method could predict the future just for a few seconds at most. However, it is difficult to properly preserve structural information using just the pixel-based model. To address this problem, our approach was to predict the semantic structure of the scene and then predict pixel-level frames using the predicted structure. This made it possible to predict the future in much longer terms, such as hundreds or thousands of frames. Here are results for several data sets, such as human dancing, car driving scenes, and so on, which involve complex dynamics and interactions between objects. We can see that the model is making quite realistic future predictions over a long period of time in both segmentation level and pixel level. We further extended this idea by incorporating geometric information in the prediction. In this work, we trained a world model for indoor scenes. In the first stage, the model predicts the semantic structure in the future by combining depth information and point clouds using 3D geometry. And then the model predicts future frames in the pixel level. This model can also predict multiple future scenarios by modeling uncertainties in the future. As you see in the video, the learn model can adapt to a new building that it has never been trained before. It can even predict what will happen in unseen locations quite well. By extending this predictive model, we are also investigating on solving robotic indoor navigation problems. So far, we looked at how to learn a world model for predicting future from visual observations. Using these techniques, the learn world model can be used for sequential control tasks by improving planning and policy learning for the agent. In this work, we developed an algorithm called Planet, which embeds the high-dimensional video observations into latent state representations, and then predict future observations and rewards for multiple future steps. Through model-based reinforcement learning, it simulates a diverse set of future trajectories and then choose actions that's likely to achieve high rewards. Thus, it can perform effective planning and policy learning just from a small set of experiences. On the continuous control task with partial observations and sparse rewards, our agent can effectively learn to solve the task by planning with learn models. So far, I have talked about how to learn a model of the world for predicting future and use it for improving planning for control tasks. Now, I will move on to ways for learning representations to improve sample efficiency and generalization. The main takeaway here is to learn representations to capture meaningful priors of the world. In order to learn optimal behaviors, efficient exploration is a key to collecting experiences that contain successful trajectories. Many methods for exploration have been proposed in deep reinforcement learning, but it is still challenging on the environments with complex observations and sparse rewards. Sparse rewards mean that successful experiences are rarely obtained, starting just from random behavior. Such property is prevalent for many real-world tasks, such as robotic control. As shown in the upper left, among Atari games, Montezuma's Revenge is a well-known hard exploration benchmark in reinforcement learning, and the agent can rarely achieve non-zero rewards, which makes it difficult to collect meaningful learning signals. We investigated state representation learning by self-supervision to address the issue of exploration. The idea is to focus on the parts of the environment that can be directly controlled by the agent's action. For example, on Montezuma's Revenge, the action taken by the agent can slightly change its own position. We leverage the attention mechanism to learn which part of the environment we can control by its action. This enables a representation of the agent's own position. With the learned state representation about the agent's own position, simple count-based exploration strategy can significantly improve the performance of existing reinforcement learning algorithms. Our count-based exploration bonus encourages the agent to visit novel positions, thus it can perform better exploration and collect highly informative data. As a result, the agent can learn a policy with better performance. And the key idea here is self-supervised representation learning. In other words, if the agent can understand what it can control in a specific environment, it will help effectively solving exploration problems. Additionally, learned state representation can be useful in more advanced exploration strategies. The low-dimensional state embedding not only helps us to identify novel states, but also it makes it possible to store trajectories of the agent experience in a compact way. We store various trajectories ending with diverse states in the memory, where each trajectory is a concatenation of the state representation. And then we explore in each of these directions and aim to discover optimal paths. Then we imitate the stored trajectories with a trajectory condition policy, which processes trajectory embeddings and learns to reproduce each given trajectory in the stochastic environment. In each specific episode, we sample one demonstration trajectory from the memory, try to reproduce it under environment stochasticity, and explore around and beyond this path. The new trajectory collected in the current episode with a novel ending state is then added into the memory. So the agent gradually expands the exploration region in diverse directions. This advanced exploration strategy helps avoid myopic behavior in complex environments and enable balancing between exploration and exploitation. In this way, our agent gains higher score on the long horizon sparse reward tasks such as Montesquieu bench. Also, the algorithm can be used to solve robotic navigation and manipulation problems with improved sample efficiency. Similarly, we can explore efficiently by abstracting the environment directly. While the previous work focused on utilizing the memory in the trajectory level, this work builds the compact graph model of the environment by representation learning. The key idea is using the successor feature to capture the local dynamics of the environment. This enables compressing the local information and obtain the abstract MDP in a compact graph form. Then the agent can reach a target state by first performing a high-level planning in the abstract MDP graph, and then executing this planned path using a goal condition policy. Once the agent reaches the edge of the explored area, the agent can perform exploration to expand the frontier. And this is in a somewhat similar way as in the previous method. Our approach achieves high sample efficiency on long horizon goal reaching tasks on complex 3D and 2D visual domains. Also, our model was able to build an accurate landmark graph of the environment and learn to follow the planned path to reach the distant goal. So far, we have seen that representation learning enhances the agent performance on training environments. But what about unseen test environments? Our research also shows that representation learning can be beneficial on unseen test environments. For example, when the visual patterns or dynamics are different in new environments, by making the representation robust to these changes or context aware from the history, the policy conditioned on this representation can maintain high performance in new environments. On tasks with various visual patterns, we use random convolutional layers to simulate the random image transformations and in colors and low-level features, and feed the input observations to train the RL agent. This simple technique can greatly improve the generalization performance of the agent in handling unseen visual patterns. On the right, we visualize the learned representations of states on demonstration trajectories. For our agent, trajectories from both seen and unseen environments are aligned on the representation space, while the baseline yields scattered and disjointed trajectories. This implies that our method learns the invariant and robust representation. We demonstrate the effectiveness of the method on unseen environments with various visual styles in several domains, such as arcade games like Coin Run, and maze navigation tasks, and robot manipulation. Another situation is when the dynamics is changing between training and testing environments. It becomes extremely challenging to learn a global model that can generalize across different dynamics. To tackle this problem, we first learn a context-aware latent representation that captures the local dynamics and then predict the next state conditionally. The novel objective here is to predict both forward and backward dynamics. Compared to existing model-based RL methods, planning with our context-aware dynamics model achieves superior generalization ability across various simulated robotics control tasks. When the environment reward is sparse, the generalization problem becomes much more challenging, as it is nearly impossible to plan in the learn model without known reward functions. To tackle this problem, we propose an action translator to assist the policy learning on tasks varying in dynamics. If the learn policy performs relatively well on one of the training tasks, then we try to transfer the good policy to other training tasks and maintain the good behavior on the target task. Therefore, we can obtain a larger and more diverse set of successful trajectories in different dynamics. Then these successful experiences can greatly help the policy learning on sparse reward target tasks. Our approach of policy transfer is empirically improves the sample efficiency and performance of meta-RL algorithms on sparse reward tasks with varying dynamics. So far, we've looked at the approaches to learn representations and models of the world for for solving relatively simple tasks. The main takeaway was learning representations and models that capture the prior, and it can be very helpful for training agents. Next, I'm going to talk about how to make these agents more scalable by solving multiple complex tasks with compositional structures. Suppose we want to build a household robot that can handle all household chores such as cooking, cleaning, laundry, and many others. The agent first needs to learn basic skills such as navigating or carrying an object to a specific location and interacting with the object, like picking and placing objects, using tools, operating home appliances, and so on. Then for solving complex tasks, especially multiple tasks, the agent also needs to combine such basic skills in specific ways to achieve such complex goals. For example, we can think about a workflow for cooking potato by boiling it, as shown in the figure, which could require the robot to find and pick up potato and then cook it by boiling and put it in a plate for serving. While both are essential steps to tackle these compositional skills, here the second problem of learning to combine basic skills is of our particular interest. One of my recent works studied how to combine symbolic low-level skills to solve complex high-level problems in a scalable manner. We assume that a complex task consists of multiple subtasks, and each subtask has a precondition. And this precondition defines the dependency between the subtasks, and the entire relation can be represented as a single graph, which we call subtask graph. Using the subtask graph, we tackle the problem as follows. The agent first explores the world to infer the dependency between subtasks in a subtask graph form. And then from the subtask graph, the agent determines the optimal order of executing the subtask to maximize the reward. Here, the performance can be evaluated in testing, and the performance can be used as a reward feedback to improve the entire process by meta-learning. the main challenge of the problem is to infer the subtask dependency structure. If you assume a symbolic representation over subtasks, then the inference problem can be formulated as the inductive logic programming problem. Thus, if we represent whether each subtask is eligible or complete in a symbolic manner, then we can learn to predict the precondition of each subtask. And then from the inferred subtask graph, we can compute the gradient of the approximate return with respect to each subtask. Intuitively, higher gradient means more likely to get higher return by performing a specific subtask. So this information can be very helpful for the agent to choose the near optimal decision. And then we demonstrated the effectiveness of the method in a simulated environment first. Here we consider a compositional task where the agent needs to explore the environment and interact with the objects in a certain way to execute the task. Even when the subtask dependencies are highly complex, our algorithm can infer the subtask graph from the agent's experience and achieve near optimal performance efficiently. In a more complex case, our method can also solve the StarCraft 2 game. The StarCraft 2 game is designed based on a so-called tech tree, which defines the complex dependency between buildings and units. Our agent can infer tech tree without any supervision, and in the end, it can win the game by exploiting the inferred task structure. This video demonstrates that the agent can collect more resources and produce more advanced units by inferring the dependencies between units and buildings, which is very helpful in winning the battle. In other words, inferring and utilizing the task structure can greatly improve the sample efficiency of reinforcement learning for some complex tasks. In fact, the compositional AI has great potential beyond games and robots, and here are some examples of real-world scenarios. For example, being able to infer the subtask dependency will help building better customer service, task scheduling, constraint planning, or in general, learning the high-level word model in the form of workflows. For example, let me talk about how compositional task learning can be applied to online shopping. Suppose there is a task of placing an order by navigating the shopping website. It is a somewhat cumbersome task because you need to perform a number of subtasks, such as entering text, clicking buttons, choosing options, and so on. Depending on the website, the details such as layouts or visuals may greatly vary, but the high-level task workflow is mostly similar. Motivated by this observation, we propose to learn a prior subtask graph over multiple similar training websites and then transfer the prior to an unseen website. In web navigation, each web element is modeled as a subtask, and then the subtask graph captures relation between each web element. Then, from the infer subtask graph, the agent can infer the required fields to fill out in order to place an order. Our recent work has demonstrated successful transfer from the previous website to a new unseen website with very high sample efficiency. Now I'd like to talk about how to make these agents even more powerful and generalizable. The key idea here is that text descriptions can allow agents to have better generalization properties. For example, language is a natural medium for humans to interact with intelligent agents. Imagine personal assistant that can understand and execute complex language queries from humans, such as check my schedule and book me a flight ticket to New York this Friday. And in another view, text descriptions can be naturally available as a signal in the form of instruction, manuals, description of environment dynamics, and so on. And agents capable of learning from such text signals can extrapolate beyond their training experience and generalize to new domains and environments with high sample efficiency. This is especially exciting nowadays due to recent developments in language understanding. Large pre-trained language models capture linguistic priors useful for learning real-world tasks. In our recent work, we show that language models can help reason about subtasks from task instructions with very little supervision. And then they help reason about object affordances. For example, the model understands that the argument of a slice action is unlikely to be a microwave. And finally, language models have systematic generalization properties, such as compositional generalization, and we can construct an agent policy that inherits such properties. In this example, even though the subtasks like pick up a knife and slice an apple were never seen together during training, the model can generalize to this unseen combination of subtasks. So far, I have talked about my research on building next generation AI for tackling complex tasks in the world. Finally, I'm going to present how learning models and representation of the world can be applied to some business problems with high impact. In December last year, I joined LG AI Research as a chief scientist, leading the AI research of the organization. Working at LG AI Research has been a great opportunity to observe how AI can be used in a business context. In LG AI Research, we learn representations from the data in business and utilize them for developing better products, services, and processes. In the business context with AI applications, there are four important elements: algorithm, infrastructure, data, and business model. LG AI Research is conducting research on the latest AI technologies and investing in the world-class infrastructure while cooperating with LG subsidiaries companies to obtain quality data and continuously discover challenging problems with high business impact. We are establishing virtuous cycles where AI research can make business impact, and thus we can invest more in AI. LG AI Research works for advancing fundamental research on AI and finding right applications of it and strengthening the AI capabilities of the entire LG group. Among these, Fundamental Research Lab conducts research on the latest AI techniques, identifies research topics that are technically relevant to LG subsidiaries in the near term, and also focus on basic research that has high potential usability in the long term. Research areas include representation learning, reinforcement learning, continual learning, transfer learning, explainable AI, active learning, time series forecasting, material informatics, large-scale AI. Within the last 1 year of establishment, we have published 18 papers at top-tier AI venues, and we developed a novel method that won the first place at CVPR 2020 Continual Learning Challenge. We continue to recruit top AI researchers to strengthen our research capability, and we also collaborate with universities and other research institutions, working together on publications and other efforts in the research community. Applied AI consists of 3 labs: data intelligence, language, and vision. We solve difficult technical problems that have high potential impact for LG subsidiaries. We develop AI methods that support business decisions, optimize R&D processes, help smart manufacturing, check product quality issues, and enhance customer value with AI-based customer care. I'll just give you one example of our recent projects in the next slide. In our efforts on fundamental research and also its application, we work on scientific discovery of materials. For example, we develop representation learning methods for designing new drugs. We have been working on discovering new lead materials that satisfy the desirable drug properties. And this is a required process before going through preclinical product development and clinical tests. Previous approaches for lead materials discovery takes about 3.5 years, dependent on human know-how and computationally expensive computer simulation. To accelerate the process, we use generative models and representation learning to construct latent space for drug candidates, and then train a prediction model that can efficiently predict the material properties. We then optimize the structure and composition of the materials in these learned prediction models. As a result, we could dramatically lower the discovery time of lead materials previously from 3.5 years to 8 months. To summarize, I have talked about my research vision and progress for building next generation AI that can potentially solve many complex tasks for humans. First, I talked about how to learn predictive models of the world from visual observations and using the learn model for efficient planning. Second, I presented several representation learning methods that can capture the prior of the world that are useful for exploration and generalization. Third, I showed how compositional learning can tackle complex tasks by combining the previously learned skills for subtasks and understanding the dependencies between subtasks. Finally, I talked about how learning representations can also be beneficial for real-world business problems in LG. So that's all for today, and I hope to present more exciting progress next time. Thank you very much for your attention.
네, General Purpose AI 에이전트에 대한 최신 연구에 대한 소개 및 이에 대한 전체 어플리케이션과 LG AI 연구원에서의 실제 적용 사례에 대해서 잘 설명해 주신 유영락 교수님께 다시 한번 감사드립니다. 질문 있으시면 질문 주시겠어요? 제가 한 가지 질문을 드리도록 하겠습니다. 최근에 앞에 김창경 교수님 강의에서도 말씀 주셨고 이용락 교수님 강의에서도 말씀을 주셨는데 결국 지금 현재 아티피셜 제너럴 AI에 대한 오픈 AI를 비롯해서 상당히 많은 연구가 되어 있고 교수님께서도 제너럴 퍼포즈를 목적으로 한 아티피셜 제너럴 AI에 대한 연구를 많이 하고 계십니다. 그러면 결국 또한 어제 백영훈 원장님께서 말씀 주신 부분에 대한 아티피셜 익스퍼트 AI에 대해서도 말씀을 주셨는데 결국 아티피셜 제너럴 AI로 가기 위해서 어떤 부분이 가장 중요하다고 생각하시는지.
예, 질문 감사합니다. 사실 그런 방향을 지향하고는 있지만 우리가 상상하는 수준의 Artificial General Intelligence는 아직 한참 멀었고요. 그냥 어떻게 보면 걸음마 단계 정도 수준이라고 생각합니다. 예, 제가 생각하는 일반적인 방향은 결국 우리가 세상에 존재하는 어떤 meaningful한 prior information을 어떻게 잘 캡처하느냐 그것에 따라서 현재까지의 그 머신러닝 혹은 AI의 프로그레스가 이루어졌다고도 볼 수가 있겠는데요. 예를 들어서 뭐 2012년에 컨볼루셔널 뉴럴 네트워크를 가지고 아주 방대한 양의 이미지 데이터에 존재하는 어떤 이미지에서 뭐 물건, 오브젝트 레벨의 어떤 프라이어 혹은 또 이미지 하이어라키에 대한 어떤 프라이어를 잘 학습을 했기 때문에 그것으로 오브젝트 클래시피케이션이나 다른 컴퓨터 비전 태스크에서의 브레이크스루를 이뤘고요. 그 다음에는 이제 최근에 뭐 프리트레인 랭귀지 모델, 즉 BERT 같은 모델이 결국 방대한 양의 텍스트에 존재하는 어떤 prior information, 특히 뭐 랭귀지 모델 등을 사용해서 그냥 주변의 컨텍스트로부터 미싱 월드를 프리딕션하는 굉장히 단순한 태스크를 가지고 학습해서 그것으로 아주 유용한 텍스트 레프레젠테이션을 얻고 그것으로 뭐 검색이나 다른 NLP 태스크에 굉장한 브레이크스루를 이뤘고 또 최근에는 GPT-3가 어떤 그냥 next word prediction이라는 굉장히 또 단순한 오브젝티브 펑션이지만 거기에 그거를 통해서 캡처할 수 있는 이 전 세계 굉장히 방대한 양의 정보들 또 어떤 거기에 숨어 존재하는 어떤 뭐 디펜던스나 콜레이션, 뭐 코잘리티 이런 것들을 임플리시트하게 학습을 해서 그것들로 지금 프로미싱한 그런 결과들을 보여주고 있고 그래서 일단 그런 방향으로 결국은 세상에 존재하는 그런 정보들을 가지고 어떻게 더 좋은 레프레젠테이션을 학습하는 것인가 저는 그런 관점에서 큰 흐름은 그것이 그런 기술들이 계속 발전하면서 저희 AI의 그 성능도 점점 올라갈 것이고 또 AGI 혹은 뭐 제너럴하게 뭐 좀 좁게 말해서 여러 가지 태스크를 뭐 일반화 성능이 높게 잘 로버스트하게 샘플 이피션트하게 학습하기 위해서는 결국 어떤 레프레젠테이션이 잘 학습되지 않으면 불가능한 일이라고 생각합니다. 그래서 결국은 그런 방향성을 향해서 가고 있다고 생각을 하고요. 예. 또 하지만 뭐 단기적으로는 저희가 이미 잘 알고 있는 어떤 도메인 알레지나 또 이미 우리가 잘 이해하고 있는 그런 구조적인 지식들을 잘 조합하면 훨씬 더 샘플 이피션트하게 학습할 수 있다. 뭐 그런 생각도 하고 있습니다. 그래서 그 두 가지를 어떻게 잘 조합할 것인가. 그래서 샘플을 최대한 효율적으로 사용하고 또 적은 양의 데이터로부터 높은 일반 성능을 얻을 것인가 그런 것들이 중요한 연구 문제라고 생각합니다.
네, 답변 감사합니다. 채팅창으로 홍지우님께서 질문을 주셨는데요. Hello, thank you for your wonderful presentation. RL seems to be sample inefficient. What do you think this problem can be solved in the near future? Do you think model free will dominate model based in complex RL tasks?
So, yeah, my thoughts are that we need a generalizable representation for RL in order to make it sample efficient. So, in the current state of the art, there is no such pre-trained representation for RL. What I mean by that is that there is no like ImageNet like pre-trained model or no BERT-like model, no GPT-3-like model in RL. So I think that's a challenge because different environments have very different visual patterns, dynamics, and so on. So it's quite difficult to capture all these diversities of complex dynamic systems. So, but at the same time, maybe if we figure out some ways to learn highly diverse and massive amounts of video data in the world, maybe such model can serve as a general purpose representation for dynamic data, especially like video based observations in the real world that might potentially serve as a representation for sample efficient RL. So, so that's my thought, but also, yeah, I don't know the answer. And maybe, yeah, let me also answer the second question regarding the model free versus model based. Again, if you have a model that captures the prior of the world very well, I think it can be much more sample efficient and generalizable. But at the same time, learning such a model is very hard. So especially learning pixel-based model is extremely challenging, and because of such a high diversity and complexity in the patterns. But it might be possible to capture some latent model or some representation space that maybe still capture some latent dynamics in this complex data. So again, maybe this is related to how we can train from complex dynamic data in a very massive large scale. And if we are able to successfully learn some meaningful latent representation, then we might be able to generalize to many tasks without having to accurately reconstruct like future pixel values, which is sort of nearly impossible in a general domain. So again, I believe that some still boils down to representation learning. So eventually, that might hold the best promise for scaling the RL for complex real-world tasks in the most general way.
네, 답변 감사합니다. 오늘 멋진 강의를 해주신 이용락 교수님께 다시 한 번 더 감사를 드립니다.
감사합니다.